continue. Let me open the table of content first. Okay. We are in chapter. Previously, we are in chapter 20, and now we will take a look at chapter 21. Okay, let me open that. Where is it? Okay, this one. Okay, beyond physical memory mechanism. Thus far, we have assumed that an address space is unrealistically small and fits into physical memory. Okay. In fact, we have been assuming that every address space of every running process fits into memory. Okay, we will now relax this big assumption and assume that we wish to support many concurrently running large address space. To do so, we require an additional level in the memory hierarchy. Thus far, we have assumed that all paths reside in physical memory. However, to support large address space, the operating system will need a place to stash away portion of address space that currently are in great demand. Okay, in general, the characteristics of such a location are that it should have more capacity than memory. As a result, it is generally slower. If it were faster, we would just use it as a memory now. Yeah. In modern system, this role is usually served by a hard disk drive. Okay. Thus, in our memory hierarchy, big and slow hard drive sit at the bottom, with memory just above. And thus we arrive at the crux of the problem. Okay, this is the crux. How to go beyond physical memory? How can the operating system make use of a larger, slower device to transparently provide the illusion of a large virtual address space? Oh, interesting. Is this the swapping mechanism? I'm not sure yet. One question you might have: why do we want to support a single large address space for a process? Once again, the answer is convenience and ease of use. Okay, why do we want to support a single large address space for a process? With a large address space, you don't have to worry about if there is enough room in memory for your program's data structure. Rather, you just write the programs naturally, allocating memory as needed. It is a powerful illusion that the operating system provides and makes your life vastly simpler. You're welcome. A contrast is found in older systems that use memory overlay, which require programmers to manually move piece of code or data in and out of memory as they were needed. Okay, try imagining what this would be like before calling a function or accessing some data. You need to first arrange for the code or data to be in memory. Iya. Okay. Oh, is this what is it called? A linear? Oh, maybe this is not about pagination, but not about paging, but about the address space itself. Okay, a single large address space. But yeah, I wonder if the single large address space is using a linear page table or the multi-level page table. Well, we will see, I guess. Aside storage technologies. Wait, let me check the table of content. Swap space, the present bit, okay. The page fault, okay. What if memory is full, okay. Page fault control flow, when replacement really occur. Oh, okay. Maybe we are also using the multi-level page table. Maybe. Okay, let me read this first before going into the aside. Beyond just a single process, the addition of swap space allows the operating system to support the illusion of a large virtual memory for multiple concurrently running processes. Beyond just a single process, the addition of swap space allows the operating system to support the illusion of a large virtual memory for multiple concurrently running processes. The invention of multi-programming, running multiple programs at once to better utilize the machine, almost demands the ability to swap out some bits. The invention of multi-programming, that is running multiple programs at once to better utilize the machine, almost demand the ability to swap out some bits, as early machine clearly could not hold all the bits needed by all processes at once. Thus, the combination of multi-programming and ease of use leads us to want to support using more memory than is physically available. It is something that all modern. What is VM in here means? Is it virtual memory or virtual machine? Maybe virtual memory. Maybe. Thus, the combination of multiple programming and ease of use lead us to want to support using more memory than is physically available. It is something that a modern virtual memory system do. It is now something we will learn more about. Okay, let me read the aside, I guess. Aside storage technologies, we will delve much more deeply into how input-output device actually work later. See the chapter on input-output device, I guess, on this persistent. See chapter 36. Okay, so be patient. And of course, the slower device need not to be a hard disk, but could be something more modern such as a flash-based SSD, solid-state drive. We will talk about those things too. For now, just assume we have a big and relatively slow device which we can use to help us build the illusion of a very large virtual memory, even bigger than physical memory itself. Okay, the swap space. The first thing we will need to do is to reserve some space on the disk for moving page back and forth. In operating system, we generally refer to such space as swap space because we swap page out of memory to it and swap page into memory from it. Okay. Reserve some space on the disk for moving page back and forth. In operating system, we generally refer to such space as swap space because we swap page out of memory to it and swap page into memory from it. Okay. Moving page back and forth. Thus, we will simply assume that the operating system can read from and write to the swap space in page size unit. Okay. To do so, the operating system will need to remember the disk address of a given page. Thus, we will simply assume that the operating system can read from and write to the swap space in page size units. To do so, the operating system will need to remember the disk address of a given page. Disk address of a given page. Need to remember the disk address. Okay. The size of the swap space is important as ultimately it determines the maximum number of memory pages that can be in use by a system at a given time. Let us assume for simplicity that it is very large for now. The size of the swap space is important as ultimately it determines the maximum number of memory pages that can be in use by a system at a given time. Let us assume for simplicity that it is very large for now. In the tiny example, figure 21.1, you can see a little example of a 4-page physical memory and an 8-page swap space. Oh, okay. 4-page physical memory and an 8-page swap space. In the example, the process proc1, proc2, and proc0, proc1, and proc2 are actively sharing physical memory. Each of the three, however, only have some of their valid pages in memory. Oh, okay. Some of their valid pages in memory. It looks like we are using the multi-level page table because only some of the valid pages in memory. Okay, rather than the entire, what is it called? The entire address space, I guess. With the rest located in swap space on this. A fourth process, proc3, has all of its pages swapped out to this, and thus clearly isn't currently running. Oh, okay. One block of swap remains free, even from this tiny example. Hopefully you can see how using swap space allows the system to pretend that memory is larger than it actually is. Okay, we should note that swap space is not the only on this location for swapping traffic. For example, assume you are running a program binary, for example ls, or your own compiled main program. The code pages from this binary are initially found on this, and when the program runs, they are loaded into memory. Okay. It's not only on this location for swapping traffic. Assume you are running a program binary, for example ls, or our own compiled program. The code pages from this binary are initially found on this. Oh, okay. And when the program runs, they are loaded into memory, either all at once when the program starts execution, or as in modern system, one page at a time when needed. Is this the code or the code page? Okay, so we might not load all the code or the instruction into the memory at once. Is that it? Maybe. Or as in modern system, one page at a time when needed. However, if the system needs to make room in physical memory for other needs, it can safely reuse the memory space for this code page, knowing that it can later swap them in again from the on-disk binary in the file system. If the system needs to make room in physical memory for other needs, it can safely reuse the memory space for this code page, knowing that it can later swap them in again from the on-disk binary in the file system. Alright. Okay, figure 21.1. Scan memory and swap space. Thing here. This is the tiny example, right? Scan memory and swap space. The physical memory only have, what is it called? 4 pages, and the swap space have, I think, 8 pages, right? Okay, block 0 until block 7. Okay, so this is in the memory, but the other page is in the swap space. Okay, this one too. Now I'm kind of curious. Are we immediately putting the unused, what is it called? The unused data, I guess, or the unused address space, the unused page from the address page, maybe that's the word. Are we automatically put the unused page into swap page, or maybe we are waiting until the physical memory is full, then we use the swap space, something like this. Do we immediately this, okay, immediately put the unused page from the address space in memory, or no, not in memory, from address space in swap space, or waiting until the physical memory to be full to use swap space. I mean, as far as I know, so far we are waiting until the physical memory to be full to use the swap space, but I'm not sure if that is always the case. We will see. Okay. Can swap later, okay. The present bit. Note that we have some space on the disk. We need to add some machinery higher up in the system in order to support swapping paths to and from the disk. We have some space on the disk. We need to add some machinery higher up in the system in order to support swapping paths to and from the disk. Let us assume for for simplicity that we have a system with a hardware managed TLB, translation look asset buffer. Recall first what happened on a memory reference. The running process generates virtual memory reference for instruction fetch or data access, and in this case the hardware translates them into physical trace before fetching the desired data from memory. Right, okay. Remember that the hardware first extract the virtual page number from the virtual trace, checks the translation look asset buffer for a match, the TLB hit, and if a hit, produce the resulting physical trace directly and fetch it from memory. This is hopefully the common case, as it is fast, requiring no additional memory access. If the virtual page number is not found in the TLB, the translation look asset buffer, that is a TLB miss, the hardware locates the page table in memory using the page table base register and looks up the page table entry, the PTA, for this page using the virtual page number as an index. If the page is valid and present in physical memory, the hardware extracts the page frame number from the page table entry, install it in the TLB, putting that in the translation look asset buffer, and retries the instruction, this time generating a TLB hit. So far so good. If we wish to allow page to be swapped to this, however, we must add even more machinery, right? Specifically, when the hardware looks in the page table entry, it may find that the page is not present in physical memory the way the hardware or the operating system in a software managed translation look asset buffer approach determine this is through a new piece of information in its page table entry known as the present bit. If the present bit is set to 1, it means the page is present in physical memory and everything proceeds as above. If it is set to 0, the page is not in memory but rather on disk somewhere. The act of accessing a page that is not in physical memory is commonly referred to as page fault. Upon a page fault, the operating system is invoked to service the page fault. A particular piece of code, known as a page fault handler, runs and must service the page fault as we now describe. Okay, let me read the aside first. Swapping terminology and other things. Okay, terminology in virtual memory system can be a little confusing and variable across machine and operating system. Okay, the terminology in virtual memory system can be a little confusing and variable across machine and operating system. For example, a patch fault more generally could refer to any reference to a patch table that generates a fault of some kind. This could include the type of fault we are discussing here, that is a patch not present fault, but sometimes can refer to illegal memory access. Right, the segmentation fault or something like that. And that make me curious, what is the difference here? How do we determine the patch is valid but not present in the memory? Maybe the next question. How do we determine if the patch is valid but not present in memory, or the patch is invalid? The patch is allocated, maybe that's the word, but not present in memory, and the patch is not allocated. At all. What is it called? Segmentation fault. Something like this. Yeah, maybe we will get an answer later on. Indeed, it is odd that we call what is definitely a legal access to a patch map into the virtual address space of a process, but simply not in physical memory at the time of fault at all, right? Really, it should be called a patch miss or something like that, I guess. But often when people say a program is patch faulting, they mean that it is accessing part of its virtual address space that the operating system has swapped out to this. Okay, we suspect the reason that this behavior become known as a fault relates to the machinery in the operating system to handle it. Okay, when something unusual happens, that is, when something the hardware doesn't know how to handle occurs, the hardware simply transfer control to the operating system, hoping it can make things better. In this case, a patch that a process wants to access is missing from memory. The hardware does the only thing it can, which is raise an exception, and the operating system take over from there. As this is identical to what happens when a process does something illegal, it is perhaps not surprising that we term the activity a fault. Okay. So the hardware raise an exception and the operating system take over. So I assume the operating system is the one that need to decide whether the patch fault is because what is it called? The page is not in memory but supposed to be allocated, or the page is not allocated at all. Maybe something like that. Okay, the page fault. Recall that with TLP miss, we have two types of system. Hardware managed TLP, where the hardware look in the page table to find the desired translation, and a software managed TLP, where the operating system does. In either type of system, if a page is not present, the operating system is put in charge to handle the page fault. The appropriately named operating system page fault handler runs to determine what to do. Virtually all systems handle page fault in software. Even with a hardware managed TLP, the hardware trusts the operating system to manage this important duty. If a page is not present and has been swapped to disk, the operating system will need to swap the page into memory in order to service the page fault. Thus a question arises: how will the operating system know where to find the desired page? Right. In many systems, the page table is a natural place to store such information. Thus, the operating system could use the page in the page table entry normally used for data such as the page frame number of the page for a disk address. Okay, interesting. Instead of memory address, we have page frame number as the disk address, I assume. Okay, when the operating system receives a page fault for a page, it looks in the page table entry to find the address and issue the request to disk to fetch the page into memory. Okay, so maybe we check if the page is allocated not from the page table entry. If page table entry and if it has page frame number, it means that the page is allocated. Either means we can use page frame number as an indicator whether the page allocated or not. Maybe something like this. Maybe so yeah, that is a new concept, I guess, for me, using the page frame number of the page as a disk address instead of memory address. Okay, it looks in the page table entry to find the address and issue the request to disk to fetch the page into memory. When the disk input-output completes, the operating system will then update the page table to mark the page as present. Update the page frame number field of the page table entry, the PTA, to record the in-memory location of the newly fetched page and retry the instruction. Right. That means maybe something like this. The page frame number can hold the memory address and disk address when using swap space. Okay, something like that. Update the page frame number field of the page table entry, the PTA, to record the in-memory location of the newly fetched page and retry the instruction. This next attempt may generate a TLP miss, which will then be serviced and update the TLP with the translation. What could alternately update the TLP when servicing the page fault to avoid this step? Right. So maybe we can also update the TLP, the translation look aside buffer, after updating the page frame number field with the memory address and then retry the instruction to prevent going through a TLP miss. Okay. See, update TLP when servicing the page fault to avoid the TLP miss. Okay, finally, a last restart would find the translation in the TLP and thus proceed to fetch the desired data or instruction from memory at the translate physical address. A last restart would find the translation in the translation look aside buffer and thus proceed to fetch the desired data or instruction from memory at the translate physical address. Note that while the input-output is in flight, the process will be in the block state. Thus, the operating system will be free to run authority process while the page fault is being serviced because input-output is expensive. This overlap of the input-output, the batch fault of one process and the execution of another is yet another way a multi-program system can make the most effective use of its hardware. Right, it is about the scheduling, I guess, from the previous chapter. Yeah, about this one, something like that. Oh, here we haven't taken a look at this because this is the advanced chapter, and if I remember correctly, we need to learn about concurrency first before reading this chapter. So there is that, but other than that, I think okay, I've read all the chapter until chapter 21 at least. Okay. Aside, why hardware doesn't handle batch fault? Hello, I wanna sleep right now. Yeah, I have operating system in my upcoming semester. Oh, nice. Well, it is an interesting topic, I guess. In case you want to read this book, let me copy this in the chat, or you can take a look at the description. I have some resource there too. But yeah, for now we will mostly focus on this book, Operating System 3 ECPs. Okay, let me read this aside. Why hardware doesn't handle batch fault? We know from our experience with the TLP that hardware designers are loath to trust the operating system to do much of anything. So why do they trust the operating system to handle a batch fault? There are a few main reasons. First, batch fault duties are slow. Even if the operating system takes a long time to handle a fault, executing ton of instruction, that this operation itself is traditionally so slow that the extra overhead of running software are minimal. Okay, wait a minute. Even if the operating system takes a long time to handle a fault, executing tons of instruction, that this operation itself is traditionally so slow that the extra overhead of running software are minimal. Second, to be able to handle a batch fault, the hardware would have to understand swap space, how to issue input-output to the disk, and a lot of other details which it currently doesn't know much about. Thus, for both reasons of performance and simplicity, the operating system handles batch fault, and even hardware types can be happy. Okay, I'm not sure about the performance stuff. I mean, that this operation itself is traditionally slow, right?
So it's what is it called? Does it even matter? Does it have a performance impact if we let the operating system handle the patch fault or not? I mean, I understand about the simplicity, like to keep things simple. For example, this one, that this operation is slow, so it doesn't even matter if the operating system is the one handling that. And also the hardware didn't need to know about the swap space mechanism, because we can change the operating system, right? And just let those operating system handle the patch fault. The hardware just need to raise an exception
if it cannot find the patch or something like that. So I kind of understand the simplicity aspect of it, but I'm not sure about the performance. Yeah. Okay. Maybe later on we will find that out, but for now that is something to keep in mind. What if memory is full? Okay, I guess we will continue this on the next session. Oh, there is some example, I guess. Figure 21.2, okay. And then also patch fault control flow, okay. Yeah, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.